So let us start with this independence of continuous random variables, say x and y. I am first going to take the situation. Yes, you have a question, please ask. If there is no question, maybe we can limit these conversations. Is there a question again? Or any comment you want to make it. Please let everybody get the wisdom of. So what? Rather than going into the mathematics straight away, let us assume that you have two independent experiments with two continuous random variables rather than discrete random variables, isn't it? Then say how do we combine the two, right? We will see. That will give us enough mathematical insight into the situation, isn't it? Suppose x and y are two continuous random variables defined on independent experiments. Idea is they have to be continuous random variables, right? So this is how we did in the discrete case, right? We combined using a multiplication. Similarly, we are going to do the same multiplication here also. I.e., in other words, you have omega x and fx for x, omega y, fy for y. These two, let us say, are given, and in general they can obviously be different. There is no reason why, as I said, this fx and fy have to be the same, nothing of the sort, right? How to combine them in a composite experiment? So composite experiment will mean what? You are performing both of these, of course, in two different corners of the room, but you are plotting the result on one plane. If x takes a value out here as minus 3 and y takes a value plus 5, you are going to put that point 3 minus 5 on the plane and say, aha, this is the value I got in the joint experiment. Just like in the discrete case, no difference, except that if you look at all the possible values of omega x, I mean omega y taken together, what is omega xy? It has to be the Cartesian product of omega x and omega y, isn't it? So which automatically implies that for the composite experiment, omega xy is always omega x cross omega y, the Cartesian product. Every possible combination will feature in omega xy. So what can you say about this region omega xy now? It has to be rectangular in shape, or it has to be maybe the whole plane is also considered rectangular in this sense, right? But essentially it has to be rectangular, not only any rectangular, it has to be aligned rectangular, it has to be aligned with the two axes, cannot be some crazy right, some rotated rectangle and so on. So this must be aligned with the axes. When I say aligned, I am talking about aligned with that, right, x and y axis. Okay, fine, that just give you intuition about omega xy. What about fxy? I will obtain fxy by taking the product of fx and fy. What does that give me? So this is all important equation now. This composite joint marginal I claim in this case is exactly the product of this. For all xy actually turns out in r squared, not just omega xy, because outside that the zeros will anyway kick in. This is 0 outside omega x, this is 0 outside omega y, and this product will be 0 whenever either x is not right outside the omega xy or y is outside omega xy. Okay, so any point outside omega xy, this will give you 0. So this is, I am just saying, this is, I am not, what I am trying to say is I am constructing, supposing I construct this function like this, I claim that this function constructed like this is the valid marginal, sorry, valid joint PDF. Think about this. Okay, so let us get going. So this is not the first time you are seeing independent random variables, right? We saw them earlier in the discrete case, and we had this property where the joint PMF was given by the product of the marginal PMS for each and every point where you had non-zero joint probability, right. In the continuous case, a very similar analogous construction holds. That is, if you want to combine two independent experiments, like for example 2 different random number generators, U01 random number generators, which is what we are going to look at, is a very important example of this. But anyway, it is true in general that if you are given x and y separately, you can always and you know that they are coming from independent sources, you can always write a joint PDF which is a product of the marginal PDFs at all points on the plane, actually using the extended definitions of the individual PDFs. So this is true even when this is 0 or this is 0, it does not matter, because 0 is always multiplyable and the product is 0. One other consequence of doing this is that this omega xy, as I was saying at the end of last class, is an aligned rectangle, always an aligned rectangle. It cannot be rotated with respect to the axes, right. So even here, what was the nature of this omega xy in the discrete case? It was an aligned grid of points. You could not just have some arbitrary crazy points which did not fall into a nice grid. In the independent case, right, it always, omega xy always has to look aligned with respect to the x and y axes. Right? There is no other way of forming it. So here you had a grid of points, nice grid. Here you have a rectangle itself, or a union of aligned rectangles. Yeah, and let me just say aligned with respect to x and y axis, right. In other words, you can get a simple rectangle like this from x1 to x2, y1 to y2, right. This could be your omega xy. This is just an example of what I mean by aligned. Why is this such a necessary condition for independence? It means that essentially for any value of y, the x takes the same set of values, x1 to x2. This is profoundly in contrast to what we had for the darts example, isn't it? When we restricted the x and y to be in a circle, as we changed the values of what x could take, the y value was shrinking or expanding. So that if that happens, then you know for sure that x and y cannot be independent. They have to be dependent. So this is a necessary condition. This omega xy looking like this is a necessary condition for the independence of x and y. Of course, it is not sufficient, it is just necessary, just gives you a picture to start with, right. And if you have the independence to begin with, then obviously if you form omega xy as a Cartesian product of omega x into omega cross omega y, you will always end up looking like this. You cannot end up looking, having any other weird shape, isn't it? Think about it, right. So, and of course aligned includes, for example, the entire first quadrant, for example, right, or any portion of the xy plane whose boundaries are parallel to the x and y axes. Of course, the whole xy plane is obviously also an extreme example of an aligned omega xy itself, isn't it? Okay. So what happens here, there is a consequence of this is that, so the consequence of this guy implies that the events x, that is these two events, x is between x and dx, and y is between small y is capital Y takes values between y plus dy. If you look at these two events, these are independent events now for every value of small x and small y. So there, this joint, if you look at the joint probability of this, so in other words, this, by the way, the joint probability is going to be fxy, xy, dx, dy. For this event, it always has this joint probability by the definition of the joint density function itself. So this, if you say it is independent, then this, then it will be what? The product of these two, which is what? Fx x dx into Fyy dy. So that is Fi. So if this factorization happens, which is equivalent to saying, of course you can always cancel these two and say this must be equal to this times this. So we say that's just justification for making this statement out here in terms of the density functions. In particular, you also have the classic textbook definition of independence, that is CDFs are also factorizable. So this is the factorization of the PDF, joint PDF. The joint CDF will also be equally well factorizable into the product of the marginal CDFs, the individual CDFs. So you have the joint, and also we have this will be this. Why do I get this? Because this is a joint probability that capital X takes values up to not exceeding this number x here, and right, jointly y takes values not exceeding capital Y. So that event is a joint event, and its joint probability is a product of these two, right? PAB equals PA into PB, just like here. So these are all equivalent definitions. This is the least useful of them. As I said, we don't work with CDFs that much, right? We just know that they are there in the background. If we need them, we will call upon them. Otherwise, we don't usually use them, right? So this is also true for all xy in the plane actually, right? Because we are using extended definitions, right? We are using a certain event, capital Fx of x can be a certain event, right? And or it could be null. All those things are always included in the definition of these guys. Similarly, this guy could be null or certain or whatever. But no matter what, right? If x and y are independent, continuous, or anyway, this is true even for this two discrete random variables. You can go and check, right, that this definition will be perfectly valid for this discrete case also. So the generality of the joint CDF is what prompts many authors and many treatments to start with that, but then they don't point out the problems of dealing with it. That's all. Okay, so this is, you can think of this as a kind of a master statement, right, which is true for all kinds of situations, right? And in fact, this joint CDF itself is general enough to accommodate some funny jumps in 2 dimensions, right? If you look at, for example, what is the joint CDF of 2 discrete random variables? It's a very complicated function. Maybe you can try to plot it with MATLAB in a 3D plot or something. It will have some crazy up jumps, at every point where every point in the plane where there is a non-zero probability, it will jump. So you can, it's a kind of a crazy 3-dimensional staircase going from 0 to 1. But try plotting it for a simple case to see, how many of you have you tried MATLAB 3D plots? Have you ever had occasion to do them? Anybody? No. This is a good exercise for you, right? To take very simple discrete example like this, right? You could take a simple, let's say x could be, take even the independent case, right? Think of just 2 Bernoulli IID random variables 0, 1, 0, 1. And then plot for that you don't need MATLAB, of course, right? You can plot the joint CDF yourself because it's just 4 points. Anyway, so the point is that this statement for independent random variables is true no matter what x and y you have, right? Could be discrete, could be continuous, could be neither fully, right? Not fully, not what did we call it, purely continuous and so on. Whereas this statement in terms of PDFs is invoked only if the PDF itself is well behaved and well, right, if it's well defined. Okay. Now the interesting twist to this is that sometimes it turns out that when you derive a joint density function, it turns out to have this property. Right? Just like how did we first start to look at independence? We took a look at a die experiment and said, well, if you look at the probability, joint probability of getting a square and an even number, odd number or something, it turned out you got 1 by 6 was 1 by 2, 1 by 3 and 1 by 2, without having two different experiments to begin with. Like that it is possible, right, we will see some examples of that, to get independence by accident. We saw it in the discrete case also. I think one of the homework problems, right, you would have seen for example, what was that, z equal to xy for uniform 0 1 in that third problem set. You would find that as x and z were actually independent, even though z was equal to x into y, isn't it? You did that thing, right? Like that you can get independence by accident also. It is not so commonly encountered, but it does happen once in a while. One important example is coming our way maybe in a week from now or something, but right, but you do get right, this equation satisfied, both these conditions satisfied without explicitly without it happening, without construction, in other words. Even so, in that case also, obviously the math is the same. When the math is the same, they are independent. You do not care whether they started out in life as independent quantity in independent experiments or whether they came out of the same experiment, does not matter. If this is satisfied, then they are independent. So basically what happens is that, well, the bottom line is very simple. For independent x and y, you have this, right, the probability that x takes values in some set A, y, the joint probability that x takes values in some set A, which, right, and A of course is just x element of A is what, is just like an interval on the x axis without regard to y, and the probability y takes some values in set B, which is some interval in the y axis without any reference to x. So this will be what, this will always be equal to the probability that x is element of A multiplied by y element of B for all sets A and B. What are these sets? These are Borel sets basically, intervals essentially.